Again I welcome you all in RC design class. In this lecture I shall discuss design example of a doubly reinforced simply supported beam. You know that so in singly reinforced section we are using the reinforcement, we are applying the reinforcement in tensile zone, but in doubly reinforced section the reinforcement are used in both sides, means tensile zone as well as compressive zone. And one another point that you have to remember, that generally doubly reinforced section is a costly section than singly reinforced section, because in doubly reinforced section we are using mass steel compared to singly reinforced section. So that's why the cost of doubly reinforced section is more than singly reinforced section. So generally the designers are not prefer doubly reinforced section, they are preferring the singly reinforced section, but in some situation they are bound to use doubly reinforced section. So what are the situation? When size of the beam is limited, okay, when the size of the beam is restricted. And another condition they should check, if the size of the beam is restricted and they have calculated the moment, how much moment comes if this applied moment, means the ultimate moment, is more than mu limiting. So in that case they should go for doubly reinforced section, and obviously the depth is restricted, okay, these restrictions are imposed. So they cannot increase the, so designers cannot increase the depth. So in that situation they should design the beam as a doubly reinforced section. And here basically we are applying the more steel in tensile zone, and also we apply steel in the compressive zone. So when we apply more steel, then what happens? Then the strength of the section is increased, okay. So the given section, the strength of the given section is increased, okay. We are using the more steel, okay, in tensile zone, and also we apply the steel in compressive zone. So you know that steel has larger compressive strength as well as tensile strength than concrete. So when we apply the more steel, then the strength of the section is increased, but at the same time it is more costly than singly reinforced section. So here the simply supported beam given of limited size 250 into 400 mm. The size of the beam which is restricted, we cannot change the depth, we cannot change the size of the beam. So this size we consider to design the simply supported beam, and with clear span of 6 meter. What is clear span? This is a face to face distance. So from face to face distance, the clear distance between the support, which is called the clear span, visible distance between the support, it is given 6 meter, and this beam rests on 300 mm thick masonry wall. This is the wall thickness is 300 mm. Now the superimposed dead load, which is applied to the beam, the superimposed dead load UDL, superimposed UDL magnitude is 6 kilonewton per meter, and another concentrated point dead load 5 kilonewton, which is applied at the middle of the beam. And what dead load is given here, the weight of beams are not considered. You know that weight of beam is treated as a dead load because the weight is a permanent load. Weight of beam is a permanent load. So concentrated point dead load 5 kilonewton, which is applied at the middle of the beam. So self weight of beam is not considered of above mentioned dead load. It means you have to calculate the self weight of beam and this load you add with dead load. And another thing is the M20 grade of concrete is M20 and Fe 500 steel. If in problem the grade of concrete and grade of steels are not given, then you have to assume the grade of concrete, and you know that for RC construction minimum grade of concrete is M20. So you may use higher grade of concrete also like M25, M30, but minimum you have to consider that is M20 as per code. And grade of steel Fe 500 or Fe 450 that you may consider. So in this problem the M20 grade of concrete is given and Fe 500 steels are given. So using those grade of concrete and grade of steel, you need to design the beam as a doubly reinforced section. So this is step 1. So in design the steps are very important. So in the step 1, first we determine the effective depth from the assumed diameter of main bar and vertical skid-up. So here the size of the beams are given. So that's why there is no need to assume any dimension of the beam, as the size of the beams are mentioned. So only you have to assume the diameter of main bar, means the main bar means tensile bar as well as compressive bar, and vertical stirrup. So size of beam which is given, that is 215 into 400, and let us use 16.5 main bar and 8.5 vertical stirrup. So you may use lesser dia, is the for main bar as per code minimum 12.5 you have to use. Okay, so you may use more than 16 like the 20, 25. Okay, but this is standard. Generally in building construction or any building construction, generally for beam, for superstructural beam, generally the 16.5 main bars are commonly used. So that's why we assume that the main bar diameter is 16.5, and also the diameter of the stirrup, that is also standard 8.5 is considered, but as per code minimum dia you may consider that is 6.5 you may consider. Okay, so here we consider 8.5, that is standard. Also we consider clear cover, that is 25 mm. The clear cover means this is the uh, this distance measured from the face of the reinforcement to the exposed surface. This height is called, similarly this one is also clear cover. Okay, so the clear cover is 5 mm. You know that clear cover depend on exposure condition. So depend on exposure condition, you may use 30-35, but this is standard for most beam. Such covers are considered as 25 mm. Next we calculate the effective depth. So how we get the effective depth? You know the definition of effective depth. The effective depth is measured from the centroid of the tensile steel to the extreme compression fiber. Okay, this distance is called effective depth. Now how we get the effective depth? 400 is the overall depth minus 25 is the clear cover, then minus diameter of the main stirrup, minus half of main dia, as it is measured from the centroid of the tensile steel, which is equal to 359 mm. Next the D dash, because this is a doubly reinforced section, so the reinforcement are used in compression side also, so that's why you need to you need to calculate effective compressive depth, that you have to find out. So this distance is called effective compressive depth. So how you get it? 25 is the clear cover, then diameter of the stirrup is, then you add diameter of the stirrup, and again it is measured from the centroid of the compressive steel to the extreme compression fiber, to the topmost fiber. So that's why the half main bar, or half of main compressive bar. So the both tensile bar and compressive bar diameter is 16.5, that we have assumed. So the effective compressive depth is 41 mm, effective tensile depth, that is 359 mm. In step 2 we calculate, so when you get the effective depth, then you calculate the effective span, because this span is very important to compute bending moment and shear forces. So how we get the effective span? Using the Codal provision that we already explained in previous lecture. So for simply supported beam, the effective span is center to center distance between the support, or clear span plus effective depth, whichever is less. So this is, here I did a mistake, 4 meter, actually this will be 6 meter, 6.359 meter. The clear span is 6 meter. We add with effective depth, and the effective depth is 6.359 meter. And the center to center distance 6.3 meter. You see that this is a center, this line passes through the center of the support. So this length is how much? 150. This length is on how much? 150. So center to center distance is how much? 6 plus 6 plus 0.15 plus 0.15 means 6.3 meter. So least value, as per code, least value is considered, so that is 6.3 meter. So here center to center distance is the least value. So the least value we consider for effective span. In step 3, we calculate combined load and bending moment and shear forces. So in step 3, we find out the combined load and we compute the bending moment and shear forces. So first we calculate dead load, and you know that in dead load one UDL is acting, another is point load is acting. So the separate load, you calculate the dead load separately and you calculate the load separately, and similarly for live load also the 5 kN per meter is given. So as the self weight of beam is not included in dead load, so we calculate the weight of beam and add in dead load. Okay, the weight of beams are not considered in dead load, so the weight of beam you have to calculate and that you add with dead load. So self weight of beam is how much? So this is size of beam 250 into 400. Then size of beam is multiplied with unit weight of RCC, that is 25 kN per meter cube. Okay, the unit is kilonewton per meter cube. So we multiply it and we get the load per meter run, means the UDL, load per meter run. Similarly the superimposed load is given, which is 6 kN per meter, and the total sum of these two load is sum up and get the total UDL dead load, that is 8.50 kN per meter. So the factor UDL is how much? That is 1.5, because the load factor is 1.5. As per table 18 for dead load, the load factor is 1.5. So the 1.5 is multiplied with total dead load, which is 12.75 kN per meter. So here point load at the middle, so this is not correct. I did a mistake. So here the 10 kN is not given, it is 5 kN is given. As per problem, 5 kN is given. So the factor point load is 1. This is 5. So 5 into 1.5 is how much? That is 7.5 kN. Similarly, the live load given 5 kN per meter, and factor UDL is 1.5 is multiplied with, as it is Limit method, as we design the beam using the Limit method. So here the factor load is considered. So for live load, for imposed load, the load factor is 1.5. So 1.5 is multiplied with live load and we get the factor live load, that is 7.5 kN per meter. So table 18, so the page number is 68. See the table. Now for computing the bending moment and shear forces for dead load and live load, so the load has to be combined, is the dead load 1.5 of dead load. This is a combined load plus dead load plus live load, which is equal to 20.25 kilonewton per meter. As the two type of load is acting, is the one UDL, another is point load. So the superposition method is used. So in superposition method, what we do, we just break the load in two component. Means the two type of loads acting. For UDL we do the analysis, and for point load we do the analysis, and these results are combined. Okay, that is simply we add the two loads, means the for UDL and for point load. Okay, so the individual separate analysis are carried out for UDL and for point load, and the results are and the analysis and the results are added. Okay, so the bending moment and this one is the PL by 4, means for UDL the maximum bending moment is W L square by 8, and for point load the maximum bending moment is PL by 4. Now these two so the analysis is done for each type of load, is the for UDL and for point load, then just we add it, okay, to get the total moments. So that is called the superposition method. As the two type of load is acting, so the superposition method are used to get the total moments. So this is for UDL, the maximum bending moment at the middle, and this is for point load, which is also maximum at the middle. So we just add it and we get the total moment, which is equal to 124.1 kilonewton meter. Similarly for shear force also, is a shear force diagram for UDL, which is linearly varying and it is 0 at the middle, whereas for point load the shear force, this type of shear force diagram comes. So so you see that the maximum shear force is occurred at the support. Maximum shear force takes place at the support, and also for point load maximum shear force occur at the support. So these two shear force we add and we get the total shear forces which is applied on beam, and those value we consider for design. The ultimate moment, ultimate applied moment is the factor moment, and U is the ultimate shear force, is the factor shear force. So we design the beam for ultimate factor moment and factor shear force. So we calculate it, we get the value of ultimate moment and ultimate shear forces. In step 4, we check the section for given size and determine area of total tensile steel and compression steel. So what type of sections comes under load? Because as I have said, although the sections are given, we must check the mathematical condition, which is mu greater than mu limiting. So in that case only we use doubly reinforced section, otherwise the section is singly reinforced if mu less than mu limiting. So we have to check the what section comes, what type of section comes. So is it singly reinforced or doubly reinforced, that we should check. of given size. So to find out, to get the to check the section, we find out we determine the limiting moment. We determine the limiting moment using that expression which is given in code on page 96. Go to page number 96 and follow this equation and find out what is the limiting moment of given section. So here the xu max by d values are given using in page number 71. For different grade of steel, the xu max by d values are given. So for Fe500, the value is 0.46. So we consider it 0.46, and we know the grade of concrete M20. The characteristic strength is 20. So all these things are known. B is known, D is already we have computed. So we obtain limiting moment is 86.1 kilonewton per meter. Again the reference are given. So you see that as mu greater than mu limiting, hence section is designed as a doubly reinforced beam. If it is less than mu limiting, then we design it as a singly reinforced section, not doubly reinforced section. As the mu is the applied moment more than limiting moment, so it means you have to design the section as a doubly reinforced section. And also the depth, the depth is limited, we cannot increase the depth. So in that case we have only one option, that is a doubly reinforced. So we should design the beam as a doubly reinforced section. Use the expression for limiting percentage of steel using equation 2.2 which is derived earlier for M20 grade of concrete and Fe500 steel. So first we find out the limiting percentage of steel using equation 2.2. So in the equation 2.2, so in balance section we just equilibrate the forces. So how we get this expression? So in balance section we just equate the forces. Instead we equilibrate the forces. Total forces is 0. We apply the force equilibrium equation and we get this relation. Where PT limiting is equal to 100 into AST by BD. Percentage of tensile steel in limiting section is a balance section which is equal to 100 into AST limiting, the area of steel used in balance section. So PT limiting is how much? That is 0.77. So PT limiting, now put this value, put this expression in that here. So AST limiting is how much? That is 691.1 millimeter square. Next we find out the compressive reinforcement. We get the compressive reinforcement using the following codal expression. So you see the codal expression. This is the codal expression. Again here the one mistakes are made. So that is FSC, Mr. Stress developed in concrete. So here one mistakes has made in code. So the actual expression is FSC minus FCC into AC. AC is the area of steel used in concrete into D minus D dashed. So you see that FSC minus FCC. So whereas FCC value is 0.45 FCK, because this is this trace is in concrete, in this trace is this trace FCC fall in rectangular portion, so the value is 0.45 FCK, whereas FSC is in the compressive stress of steel for corresponding strain epsilon SC, okay, strain in the concrete where the compressive reinforcement is placed. So at this level, what is the strain? So that we calculate, and the corresponding stress we have to find out. Okay, you need to find out the FSC for the corresponding strain by the square. So if this is a section, the compression steel, so at this level, what is the strain that we calculate? So the strain value, again this expression is already, we have explained how this expression comes, or directly you can use the direct IS 456 equation. You can use the IS 456 equation to get the strain value, so which is equal to, again it is given in page 96, the epsilon SC, which is equal to this, using that expression to find out the strain at the compressive reinforcement, but the compressive reinforcement is placed. So at this portion, so what is the strain that you get using that expression? So this expression we get simply using the linear distribution of strain diagram. This is epsilon SC, this height you know, okay. So this height is known, that is XU max. So we get the expression epsilon SC where the compressive reinforcement is placed. So at this level, what is the strain? Using that expression, we know that XU max by D is equal to 0.46 for Fe 500 steel. So XU max is how much? That is 165.1 millimeter. So epsilon SC is equal to 0.00263. So corresponding FSC is how much? 407, which we get from the SP16 table A, page 6. Show you. So that value the value is 0.00263. Now for you see that this is a stress strain diagram of cold work deform bar. So here in SP16 this table is prepared for different stress level, for different strain, what is the stress value that they have given using that figure. So you can also prepare this table. So this is given in SP16 page number 6. So for different stress level, like this value is between 0.263, so it means this value is between 0.00226 and 0.00227. Now that this is an intermediate value, so the linear interpolation has been made for getting the intermediate values stress. Okay, the actual strain is 0.00263, so which is between 266 and 277. So the linear interpolation is made, or from this graph also you can get the value. Okay, so for different stress the value for different, so you see that for 5FY the strain is how much? 0.001. Similarly for 0.9FY strain value is 0.003. Okay, so better you use this SP16 table to get the stress value of corresponding strain. So the interpolation is made. So the linear interpolation is made, and we get the value for 0.00263 is how much? So this is for 0.0226391, 0.00227 413. So for 0.00263 is how much? That's so for just you do the linear interpolation and you get the value. So this value we calculate, that is 407 MPa, which we get from SP16 table A, page number 6. You see that this table is prepared from this diagram. From the stress strain diagram. This table is prepared in SP16 for FY 415 and FY 500. So the corresponding stress we are getting the strain value, we are getting the stress value, and the linear interpolation is made if the value is between any two successive values. So we do the interpolation and we get the corresponding stress. So compressive reinforcement is obtained using the following codal expression. FCC is this, that we already explained. Epsilon SC is this, so corresponding FSC 407 MPa. Now the ASC is how much? That is 299.45 using that expression. Okay, so using that expression we get the compressive steel used in section. So this is the required steel we get. This amount of steel is required. Next, the additional area of tensile steel is obtained by using the following codal expression. Again we use the codal expression. This codal expression are used. This AST2, already we have calculated AST1, which is the limiting area of steel. This balanced area of steel we already calculated. Then AST2 how you get? Again using that expression. So this is equal to, again here the mistakes are made. ASC, the actual expression is ASC into FSC minus FCC divided by 0.87 FY. Okay, so this rectification, you do this rectification because this is the mistakes are made, so the FCC has to be subtracted. So it's the actual expression, the codal expression, only the FSC are given, but the actual expression is the FCC has to be considered. That we already explained, we have explained in doubly reinforced in previous lectures. So using that expression, codal expression, we find out the area of steel used is the additional area of steel we get, that is 273.9. So the total tensile steel is how much? That is AST1 or AST limiting plus AST2. So we get the total steel 965 millimeter square. So this amount of steel is required that you have to apply in tensile zone to sustain the load, and this amount of reinforcement used in compression side. Okay, these are that you have to provide. This much of steels are required in the compressor zone to sustain the load. Okay, so in doubly reinforced section, the tensile steel we get, and also the compressive steel we also get, that is 299.45 millimeter square. So the total tensile steel, so just following the codal expression, codal provision, codal guidelines, we get the total area of tensile steel and total tensile steel and the compressive steel. How much tensile steel is required, that you have to apply at the bottom, and how much compressive steels are required, which you need to apply at the top. Okay, that we calculate using the codal expression. Following the just codal expression, we get the value. Solving the equations. Now the diameter of the main bars are used 16 mm. So the how many bars are required? That is required by area of single bar. Area of single bar is 5 by 4 16 square. So how many? 4.80 number. So which we cannot provide. Okay, it's a number you cannot provide. Similarly, the compressive steel is required at top, 299.45 millimeter square. Diameter of main bar. So for tension and for compression in both side, we use same main bar, same dia. We are using the same dia. So the diameter of the main bar is 16 mm. So number of bar is required. How much? How many? That is 1.49 numbers. So let us provide 5 numbers 16.5. So as we cannot provide 4.8, so we provide 5 numbers 16.5 main bar at the bottom and 3 numbers 65. So it comes 1.49. So we provide 3 because as we apply 5 numbers at the bottom, so at top at least 3 bars you have to provide. So 3 numbers 16 by 5 bars are used at the top. So AST provided is how much? That is 5 into 5 by 4 d square, and the PT provided 100 into AST by BD, 1.12 percentage of tensile steel of doubly reinforced section, and similarly AC provided this and PC provided 0.67. Next we check minimum and maximum reinforcement. The court said the what reinforcement you apply that should fulfill minimum and maximum reinforcement. Okay, so the minimum reinforcement is given in court. So we cannot use the reinforcement that should not be less than minimum and should not be more than maximum. It should be within minimum and maximum. What reinforcement we provide, that should be within minimum and maximum. Okay. So as per the following codal expression, so here the minimum reinforcement given, it is given in clause number 26.5.1.1 is the given by the following expression: AS by BD equal to 0.85 FY. So we calculate the minimum steel that is required 152.6 millimeter square, and the ASP provided is how much? That is 1004.8 millimeter square, which is more than minimum. Okay, so it means hence okay. Again, maximum tensile reinforcement as per code, you see that for maximum reinforcement, area of tensile reinforcement shall not exceed 0.04 BD. Okay, B is the width and D is the overall depth as per code. So the maximum reinforcement, again we check, that is 4000 millimeters. So what reinforcement we provide, that should be within minimum and maximum. So ASP provided is less than minimum and as well as more than minimum as well as less than maximum, hence okay. For maximum area of compressive reinforcement as per code, this is 0.04 BD 4000. Again AC provided 602.88 millimeter square, which is less than AC max, which is given in code. Maximum reinforcement, compressive reinforcement are given in code. So we check it and we find that it is satisfied. So hence okay. So in step 6 we check the deflection. Okay, how we check the deflection? The deflection limit is given for different beams in clause number 23.2.1. the for simply supported beam, for different type of beam, for cantilever 7, for simply supported this is 20, for continuous it is 26, and the span which is up to 10 meter. For more than 10 meter, this provision given. So in this problem the span is less than 10 meter, so we use this provision for different beams. Okay, so this beam is simply supported, so this value we have to consider, this is allowable value 20. Now depending on the area of stress of steel for tension, the value A or B shall be modified by multiplying with the modification factor. Again, depending on the area of compression reinforcement, the value of span to depth ratio be further modified by multiplying with the modification factor obtained as per figure 5. So in figure 4 the modification factor, we get the modification factor from the figure 4, and this modification factor is multiplied with the above value, and for compression reinforcement the modification factor is computed and the modification factor is multiplied with the above value. So this is the expression for allowable as per code. The modification factor KT is the modification factor for tensile reinforcement, KC is the modification factor for compressive reinforcement. Now to obtain KT you need to calculate PT and FS. The FS value, this expression is given. So PT is how much? The AST is provided. So the PT provided is 1.12, and the stress developed in steel, tensile steel, using the following expression 0.58 into Fy yield stress into AST required by AST provided. Required is 965 and provided is 1004.8. So the value stress of steel is 278.5 MPa. Now you see that now this stress value, so the in figure 4 for different steel stress, different Fs, the different parabolic curves are drawn. Like this one is for Fs 120, the minimum stress value is 120 and maximum is 290. So for different stress value the curves are drawn, and here, so in the figure 4, the x-axis is represented by the percentage of tensile reinforcement and y-axis is modification factor. Now the value is 270, so which is between 240 and 290. So we draw a curve between these two. Okay. Now the PT is how much? 1.12. So it means, so here this is deviation is 0.2, 0.4, 0.6, 0.8, and this is 1, then 1.12. So means this one, this value, this point. Now we draw a vertical line which intersect this assumed curve. Okay, now this point we project on x-axis, project on ordinate, how much? That is approx 0.94. So approximately you calculate this value. Okay, not exact. Calculate this value. Calculate modification factor approximately. So that is 0.94. From figure 5, find out modification factor for Kc. The Pc we already get the percentage of compressive reinforcement is provided 0.67. So for 0.6, so here you see that again this x-axis represent percentage of compression reinforcement and y-axis representing the modification factor. So PC is 0.67, so it means here the ease deviation is 0.25, so it's 0.67. So this is 0.75. This value, draw the vertical line and project on x-axis, and which cut this point, and see approximately 1.16. So now the values are multiplied with allowable value limit 20, so we get the 21.58. Now the L by D provided is L means the effective span, which is 6.3 meter, and D is the effective depth, which is 12 to 359. We get 17.5, which is less than L by D allowable. So hence, okay. The reference given, page number 37, go to page number 37, 38 and 39. The clauses, you check the clause and check the figures. So L by provided is less than L by D allowable, hence okay. Now in step 7, after checking the deflection and checking the minimum maximum reinforcement, now you design the shear forces. So first you compute the shear forces, which is tau v is equal to u by bd. Okay, this expression is given in page 72 and 73. So find out nominal shear forces, then find out percentage of tensile reinforcement, so which we have already calculated for the what steel we have provided, and we get the corresponding percentage of tensile reinforcement, that is how much, 1.12. Now for M20 grade of concrete, and tau c value is obtained from table 19. So the value is 1.12. okay, so you see that the percentage of tensile reinforcement are listed below. So this 1.12 is between 1 and 1.25. now the grade of concrete is M20. okay, so now this value is between 1 and 1.25. so for intermediate value, linear interpolation is made. okay, so the linear inter for 1. So this is 0.62, 1.25, 0.67. so what is the value for 1.12? the tau c value is how much, that you find doing the linear interpolation. Now we obtain the tau c value from the table 19, that is 0.65 MPa. so now the tau v is more than tau c, so it means the shear reinforcement is required as per code, and the different shear reinforcement are used in different forms, like the vertical skid-up, bent up bars, inclined skid-ups. So now we are using the vertical skid-up, so which is most commonly used skid-up. The vertical skid-ups are commonly used. So the vertical skid-ups are used here. So for vertical skid-up, the provisions are given to find out the spacing of the skid-ups using this codal expression. Now area of skid-up leg. So the two-legged skid-ups are used. Two-legged skid-ups are used, and diameter of the skid-up is 8.5. The two-legged 1 and 2. So the area of vertical skid-up leg is 2 into pi by 4, 8 square, and it is equal to 100.48 millimeter square. Now using that expression, this expression is given in code. Okay, see the reference. This value is given, v minus tau cbd, which is equal to 0.87 fy asb into d by sb. asb is the area of vertical skid-up legs, d is the effective depth, and sp is the spacing of the skid-ups. Now using the codal expression, we find out we get the spacing of the skid-up, which is equal to 1712.5 mm. But as per code, the maximum spacing of skid-up is 3D or 300, whichever is less. Now 3D is 3 into 359. Again, here I did a mistake. That is 359. So 3 into 359 is 1077 or 300, whichever is less. So let us provide two-legged 85 skid-up at the rate of 100 center to center. Because you see that here the although 300 comes, maximum is 300, but we provide 100 because to get the better confinement of the bar, such closure spacing we have used, and these are basically standard spacing which are used in site. And if I use the closure stirrup, so it means the reinforcement are confined and it will not displaced under when the concreting are done, so that time it will not displace, the bars are not displaced. So this is standard spacing, use this one 100 center to center. So these closure stirrups are so this confinement is beneficial for earthquake resistant structures also. So for the to make the earthquake resistant structure, you need closure spacing stirrups has been used. So this is another aspect to make the earthquake resistant, because in every structure the earthquake force has to be considered, earthquake criteria has to be considered. So considering the earthquake effect in structure, the closure stirrups are used, which is 100 center to center. That will confine the structure, that will improve the confinement of the reinforcement, so which improve the earthquake which improve the earthquake performance, okay, which improve the earthquake performance. So it will increase the earthquake performance of the structure if I use the closure stirrup. So that's why we provide 100 center to center. So here the all codal provisions are given. So generally the vertical stirrup which are commonly used, inclined stirrups are not used, but in some special case such type of stirrups are used. And the bent up bar, in the past time such type of bars are used. But nowadays the vertical stirrups mostly used in RC design, in RC construction. Next we check the development length. This is the expression given in code. You see the page number 42 and 43, where the provisions are given development length. This provision is given in clause number 26.2.1. Now development length is 5 del s is equal by 4 tau bd. 5 del s is 0.8785. So tau bd is taken from IS 456 for M20. It is similar as I have discussed in previous lecture. Tau bd is taken from IS 456 for M20 grade of concrete. It is 1.2 Newton per millimeter square, and the above value is increased 60% for deformed bar. These provisions are given. You see that here for M20 it is 1.2, and for deformed bar the 60% is, so 1.6 is multiplied with 1.2. 1.92, so the LD is 56.65, which is 905.67. As per code said that development length should be less or equal to this amount. So M1 is taken from step 6. The main bar is anchored into the support. Here standard 90-degree bend is used, because this bar is anchored, 90-degree bend is made, so at the end. So that's why the anchorage development anchorage value is increased. So for 90-degree bend the anchorage value is 8.5. As per code, for each 45-degree bend the 4.5 has been increased. So the 90-degree bend means 8.5. And here the M1, so approximately, because this value is very large, the big value comes, so that's why to simplify the analysis, we consider this is actually the moment resistance that you have to calculate. So in doubly reinforced section, it will take time, or it is so the lengthy calculations are required. So but for approximately, you can consider the applied moment. V is the applied shear force, although it is resistance, but this value is large, so that's why we roughly check. Okay, the M1 value we consider 124, which is the applied moment, and the 67.5 is the applied shear, and this is the anchorage value for 90° bend, 96 mm. So it means this comes, so hence LD less or equal to this, so hence okay. So codal provisions are given. So these are reinforcement details of simply supported doubly reinforced beam. Longitudinal, this is a longitudinal reinforcement details. Stirrups are used. The spacing of the stirrup is 100 cm to center, and diameter of the bar is 8.5. So you see that this bar is extended here because the stirrup is stirrups are placed around the bar. So that's why this one is this length is this diameter will come, or diameter of the stirrup will come on the longitudinal view. So it's 8 mm. Okay, now the spacing of the stirrup is 100. 90° bends are used. Cross sectional view. Here you see that at bottom 5 numbers 16.5 are used, and at top 3 numbers 16 bars are used, and the bar is anchored. The stirrups is around the main bars, and it is anchored in the compression zone. Okay, so the sagging belly movement takes place. So it means the reinforcement should apply at the bottom because tension developed, and for strengthening the section we apply the steel in tensile zone and compressive zone. As we design the beam as a doubly reinforced, so the additional steel apply in tensile zone, and in compression also the steel are used for to increase the strength of the section. So 3 16s are used at the top, and the two-legged stirrups are used. Vertical 8.5 stirrups used. Diameter of the stirrup is 8 mm and 100 cm to center. So this is the design problems I have discussed of doubly reinforced section. If you have not learned, so before design I advise you that you must know how the doubly reinforced sections analysis are carried out, how the doubly reinforced sections analysis are done, and the theory you must read properly, thoroughly, and then you start design, because there are a lot of equation we use, number of equation we have used, which we have derived when we analyze the beam. So that time we have derived all the expressions, so you check it, and the design we have done. So this is assignment 4, assignment for RC design and RC design seasonal. Make one copy for each theory and seasonal. Design a simply supported beam. Again the limited size 350 mm given with clear span 5 meter, supported on 300 mm thick wall, superimposed load 5 kN given, live load 4 kN given, is subjected on beam a concentrated point dead load, that is 4 kN placed at the middle of the beam. Self weight of beam is not considered of above mentioned dead load. Use M20 grade of concrete and Fe450 steel. Draw the details reinforcement in scale. Okay, this is the assignment I have given. so that you submit. So that I tell you that we discuss with your seer, and when you have to submit the assignment 4, that I shall tell you. So here I end my lectures. In the next lecture I shall discuss the design of continuous beam, how the continuous beams are designed, because you know that mostly the beams are continuous, having more than one span. So how the continuous beams are designed, that I discuss in next lecture. Okay, thank you.